So today we will study about sedimentary texture. Um, the term sedimentary texture means that is the pattern formed by the sedimentary grains during their deposition. That is the all the sedimentary particles, how and which pattern they show uh, during and after their deposition. That is called, or that is known as sedimentary texture. Now there are certain characters or certain um, things which will describe the texture of a sedimentary rock. The first and foremost thing which will describe the sedimentary texture, that is the size. Second is grain angularity, or often it is called grain roundness. uh, that is written here in the third point. And another is the sphericity. Fourth is the shorting. Now, together all these textural properties, they will reflect about the process operating for the deposition of those sedimentary particles, the nature of the source rock or the nature of the parent rock, the climatic condition, the depositional environment. So together, by studying all these textural properties, we can get an idea about the depositional condition, depositional medium by which these grains are carried out and deposition occur in a basin, as well as the climatic condition and nature of the source rock. So we'll start one by one. Now, uh, differences in texture. So as we know that every natural medium like the wind, water, glacier, they have their different properties. That is their specific gravity, their density, their flow velocity. So depending on that, they will generally carry different size of sediments, and there are other things that also vary with these mediums. But first and foremost, what we easily understand, that is the variation of size within different natural mediums which they are able to carry. So depending on different sedimentary conditions, that means sedimentary conditions means your depositional medium, depositional environment, um, depositional climatic condition. So depending on these um, various conditions, your sedimentary grains texture is changed in different areas. So that means the texture of the sedimentary rock is will be different in different sedimentary depositional condition. And by observing these different sedimentary textures, we can relate them to their mode of formation. Now, first and foremost texture which we already previously studied, that is the sedimentary size. So this is the firstly proposed and till date the most accepted sedimentary size classification, that is the Arden-Wentworth grade scale, which is a modified versions of the previously published Arden scale, and this scale is published in 1922. Here all the sedimentary grains are classified depending upon their size or depending upon their diameter, and each size class is proposed as a function of 2. So either it is 2 to the power something like 2 to the power 1, 2 to the power 2, 2 to the power 8, or it is a fractional value of 2 to the power, okay, like 1 by 2 to the power 1, 1 by 2 to the power 2. So every size class you will go either it is increasing side or decreasing side. You will, the size class limits are in the uh, powers of 2. And depending on that, Ardent Wentworth classify the sedimentary size into 7 groups. The smallest unit in which the sedimentary particle size is less than 1 by 256 millimeter in diameter, that is known as clay. The higher size is known as silt. After that, sand, then granules, pebble, cobble, and boulders. So these are the 7 size class proposed by Arden and Wentworth in 1922. Later, Crambin proposed a 5 scale because of the necessity of then times mathematical calculations, in which time computer and calculator is not so much available. So Crambin proposed a 5 scale by logarithmic transformation of these size values. But later time, when the computer and calculators are very much available to us, then people again goes back to the uh, firstly proposed Arden Wentworth grade scale, and till date it is the most acceptable, most renowned sedimentary size classification. So by the help of this size, we can get an idea about the sedimentary depositional conditions, such as the coarser particles like the boulders, cobbles, pebbles, granules, they are deposited close to the source rock. Suppose a river originating from a hilly region, and it will meet in a sea. So near its source, near the hilly region, you will get this coarser size, sedimentary grains. Now, as we move away from the source region, you will get finer and finer rocks. In the middle course of the river, you will get sand deposition. And ultimately, when the river meets with the sea, you will get silt, and little deeper part of the sea, you will get clay deposition. So, as we move away from the source rock of any natural flowing medium, the sedimentary grain size will gradually decrease depending on, or this grain size decrease is directly related to the decreasing energy condition of the flowing medium. So the energy condition of a flowing river is maximum near the source region, that is near the hilly region where the altitude difference is maximum. But when it reaches the flatland, the plain land, its altitude difference becomes very low. So energy of a river will fall drastically, and in the plain lands the flowing speed of a river is very low with respect to the hilly region. So in that condition, a river will not able to carry these larger size particles, so they deposited before uh, flowing in the plain land, that is just touching the plain lands. These larger size particles are deposited, that means river is not able to carry these large size particles. But at that condition, in the plain land condition, river can carry this sand, silt, and clay size particles. So gradually, as we move away from my source rock, any natural medium, depending on its decreasing energy condition, the grain size which will be deposited in an area uh, or in the flowing path of that natural medium is also decreasing. Okay. Second property, that is known as grain angularity, or in another term, grain roundness. Basically, this angularity and roundness, these are two opposite meaning terminology. So angularity and roundness are not same. They mean two opposite things, but both of these terminology are used to depict a single property of any grain. Now, the term roundness, or you can say angularity, is concerned about the curvature of the corners of a grain. Say for example, this grain if you consider two sides, this one is a side and this one is another side. Now these two sides meet along here, this corner. Now this corner's curvature, whether it will be a sharp contact, sharp corner like this, sharply angular, or it will be gently curved down to the another side, this side gently curved down to another side. So this property, whether it is the corner between two sides is very sharp or it is gently curved, that is known as roundness or angularity. Okay, so when it is sharply cornered by the two sides, then you can say that angularity is high, or in other terminology, that is roundness is low. And when it is gently carved to other side, then you can say roundness is high but angularity is low. So the terminology angularity and roundness are opposite, but they are depicting the same character of a grain. Okay. Now how do you measure roundness? Basically, if we consider an irregular grain, you can see that there are numerous numbers of sides, numerous small sides generated in an irregular grain. Now roundness indicates that it is a ratio of the average radius of curvature of the edges along the corners of the grain to the curvature of maximum inscribed circle within the grain. I will explain this. Now, if you consider this irregular grain, there are numerous corners you can see. So, along these corners, if you consider small circles, each circle have a radius. Okay, so you can see that here is a circle, here is a circle, here. So lots of circles are possible along the corners, and each circle have a radius. Now, if we sum all those, if we add all those radius, that will be small r, and the number, total number of radiuses which will be added, that is n numbers. And this n may be 10, maybe 20, maybe 50, any number would be possible. So summation of all these small circles radius which occur along the corner of the grains, divide by the total number of countings or total number of these possible circles occur along the corners of the grains, that is summation of RT with sigma n by total number of countings. This value is put in the numerator and this is divided by the capital R. This capital is R is the maximum radius bearing circle which is possible to draw inside this grain. Now here you can see that this R value with this R radius, that is the maximum circle which is possible to draw inside the grain. Below this R value, here you can also draw a circle, but that is not indicating or that is not having the maximum radius value. So this R radius value bearing circle is the maximum inscribed means occurring inside the grain, inscribed circle possible within this irregular grain. So roundness is depicted by summation of the smaller circles radius divided by total smaller circle countings. This numerator value is divided by the maximum inscribed circles radius, that is R. Now the roundness varieties or the roundness property of a grain, they can be depending on the calculation of the previously said formula. They can be of different types starting from the very angular to subangular, sub-rounded, rounded, and well-rounded. Here you can see that the corners between two surfaces in this grain is gently rounded or smoothly rounded, and this smoothly changing of one side to another side is maximum here, so that is why it is called a well rounded. So be specific or keep it in mind that rounded does not mean that it will be a perfect circle, it will be like a ball. No, that is not rounded. Roundness means the angular portions or the junction portion between two sides, this one side and this sides, these two sides must have been say smooth curvature. If the curvature is very sharp like this, here this side and this side sharply meet with each other, then we call them as angular or subangular grains. When this curvature is smoothly changed to another side, then we call them as rounded or well rounded, moderately rounded, like those. Now a grain, if its physical and chemical condition of two grains remains constant or remains same, then the grain which have larger in size, that will be more rounded, because this roundness basically is related to the abrasion of the grains. When a grain is transported along the medium, it will collide and abraded with the bottom substrate as well as along the other grains, along with the other grains. So as much as abrasion is occurring within a grain, within the grain during its transportation, the grain becomes the angular portions, those angular portions between those two sides, that become more and more rounded. So a large crust, because of its large superficial area, during transportation there is more chance that it will came into contact more times with the bottom substrate and other grains within the medium. So that is why these large clasts will be more regularly or more frequently abraded during transportation. So they have more tendency to become more rounded. Whereas a smaller clast or a softer clast, basically this will be smaller, a smaller clast, because of its lower surface area, it has less probability or less chance to collide with other grains or to collide with the bottom substrate. So that is why the roundness value of a smaller grain will be lower uh, compared to a larger clast having same physical chemical condition of those grains. Now this roundness, generation of roundness or angularity, that will also depends on the physical stability or durability of the grain. Suppose a grain having two or three sets of cleavage, so during transportation, when they collide with each other or collide with the bottom substrate, then there is a very pronounced chance that this grain having two or three sets of cleavage, they will split along the cleavage planes, such as your feldspar, a calcite. Those have very pronounced two or three sets of cleavage. So during transportation, when these grains are collide with each other or collide with the bottom substrate, these grains have a chance to break along the cleavage planes. So chances of being rounded become smaller. But if the same sized grain is of a quartz, we know that quartz does not have any cleavage. So with transportation, there is almost no chance of breaking that particular quartz grain along certain previously developed weak planes, because quartz does not have any previously developed weak plane or cleavage plane. So chances of being more and more roundness is greater in quartz compared to in feldspar compared to calcite or other grains. So more and more weak planes occur in a mineral, its chances of getting well rounded is poor. Whereas a grain or a mineral having less number of or no cleavage planes or no previously occurring weak plane, it will be during transportation become more and more well rounded. Now, as this roundness property or angularity property is dependent on the frequent abrasion process during transportation, so it is a general thing that as much as long distance a grain will travel, so as it will came into contact with other grains and with the bottom surface more and more, the less distance a grain travel, it will came into contact with other grains at bottom substrate lesser times. The more distance a grain will travel, it will came into contact more with the bottom surface substrate and other sedimentary particles. So this degree of roundness, that means more and more rounded grains, that will also tells us about how much distance a sedimentary particle is transported from its source area. So if you get angular cluster of the same composition like this one, you can say short distance transport from the source. If you get rounded or well rounded cluster, you can say distance of transport from the source is large. But keep in mind or remember it, whenever you try to compare these things, whether a grain is angular or whether a grain is rounded, make sure that the composition or the mineral is same. If you try to compare a angular feldspar with a rounded quartz, then maybe your interpretation is erroneous. So for comparing this degree of roundness of any two grains, it will better to be within the same mineral if the two grains are of same mineral. If the mineral varies, then depending on their physical durability, their degree of roundness is also changed. Now next term is the sphericity. So if we go to the previous slide, then we previously taught that roundness or angularity. So in that case, roundness and angularity, whatever you may call, that will be determined in two-dimensional sections where two sides meet in a corner, and that corner, whether it is a angular or smoothly curved, that we call angularity or roundness. Now here comes a three-dimensional property for which three sides or three axes of a grain you have to see. So sphericity is basically it's a measure of how close a sedimentary grain is of a sphere, a perfect sphere like a cricket ball, like a football. So sphericity is close to a sphere, not a circle. So sphericity will be observed in three-dimensional. So all the axes, that is length, breadth, and width, you have to see. So for a perfect sphere, all these axes A, B, and C are of equal in length. But for not a perfect sphere, that is if you consider a egg or if you consider a rugby ball, the rugby ball is well rounded, but it is not a sphericity of the rugby ball is not high because it is not close to a perfect sphere, but roundness is high. So a grain may be well rounded. Look at these grains, that shape is almost nearly to be a rugby ball, an elliptical grain. So this grain is well rounded, but sphericity of this grain is low. But in this case, a cricket ball or a football, the grain is well rounded as well as sphericity value of this grain is also high. In this case, the first figure here, the grain is angular, but sphericity value is high because this grain is much more close to a sphere with respect to the bottom one. Here almost the A, B and C axes are almost close to each other. The grain may be angular, but sphericity value is high. But here the grain is also rounded, sphericity value is also high. Here grain is moderately rounded, sphericity value is low. Here grain is well rounded, but sphericity value is low. Okay, so remember the thing that roundness or angularity is observed in 2 dimension, whereas for sphericity you have to observe it in 3 dimension. So under microscope you will observe the roundness property, and sphericity cannot be observed under your petrological microscope because it is a thin section. You can only get two axes, either it will be A and B or B and C or C or A, but the third axis is missing under your petrological microscope. So for telling sphericity of any sedimentary grain you have to observe in hand specimen. Okay. Next property for detecting texture or for telling texture, that is called the shape of a sedimentary grain. So for telling shape, there are numerous classifications schemes are available, but till date the most acceptable and most used shape terminology is proposed by Zing, that is in 1935, where Zing take the ratio of the axes of any grain. Zing draw a biaxial diagram in which he take the x-axis as the short axis by intermediate axis, the ratio of short axis by intermediate axis, and along the y-axis he plotted the intermediate by long axis. So in x-axis he plotted c by b ratio, and in y-axis he plotted b by a ratio. So with these values, Zing proposed the shape differentiation of any sedimentary grain. Now, with these two axes, Zing divided the entire field into four areas, and in every axis, in the two-third portion of the axis, Zing marked a boundary that is 0.66 value from. So this axis is from 0 to 1, and this division is plotted in 0.66 um, points. Again, here in the x-axis, this is from 0 to 1, and the division value is 0.66. Now, according to this biaxial diagram, the top left corner, the shape is known as discoid or oblate. What the actual properties are there? Here you can see the any two axes are almost equal in length, but the third axis is smaller with respect to the other two. If you consider its two axes is this axis and this axis is almost same in length, but this axis is smaller compared to the other two. So this type of shape is known as oblate. In mineralogical terminology, mineralogical form, you call this type of shape as tabular. The in the top right sector, the shape of the grain is known as equant, where all the sides, all the axes of the grains are equal in size. We are often called this kind of shape as cubic shape. So this is a like a perfect cube where all the axes are of equal in size. In the bottom left, this type of shape is known as bladed. So what is the difference between bladed and oblate? In bladed, you can see that one axis is extremely high value and the other two, the one is intermediate with respect to the higher one axis value, and the third axis which is extremely narrow, that is like a blade, saving blade of ours. So in that condition, the third axis value is extremely low or almost negligible with respect to the other two, and among the other two, one is higher, having much higher values than the other. So among these two, one is higher values and one have lower values, and the third axis is extremely thin or extremely lower values. In the bottom right corner, the shape is called rod like or prolet shape, where one axis is extremely high and the other two is almost equal in size. So this is showing a rod shaped, rod like shape, this type of shape. So depending upon the ratios of the three axes of any uh, three-dimensional grain, Zing proposed this type four sedimentary grain shape. One is oblate, equant, roulette, and bladed. Next is sorting. So what sorting means? Sorting means that the grain size distribution of any sedimentary rock, whether it will show same size grain size distribution or of different size grain size distribution. In this picture you can see that the left hand picture, where the grain sizes are almost same in size, all the grains are all same in size, whereas in the right one picture you can see that there are different sizes of grains. Some are larger, some are very smaller, and some are medium in sizes. So the left one figure here, as all the grains are of equal in size, so you can call them as well sorted or sorting is high, whereas in the right hand picture where there are different sizes of grains, you can say it is poorly sorted or ill sorted, or simply called the sorting is poor here. Now a well sorted particle means, that means there are almost all the particles are of same size, so it indicates that for during deposition of those all size particles, there is constant current strength for a long periods of time. So for a long time, same energy condition of the depositional medium is occurring there, whereas where you get poorly sorted grains or ill sorted grains, that is of deposition of different size particles, then you can interpret that with time the current strength or energy condition of the depositional medium is fluctuating. So sometimes it is higher, during high energy condition larger grains are deposited, and sometimes it is very low, that is very calm. So during that time the finer particles are deposited. So depending on this energy condition variation, uh, your grain sizes will also vary. So whenever you get well sorted grains, that means a constant current strength occurring for a long time. Whenever you get poorly sorted grains, that means a fluctuating energy condition is occurring with time. Now you can see that with um, changing energy condition of a flowing medium, in this case here it is showing as river. So you can see that as the river is moving from the hilly region to flatland and then into the sea, the grain size is decreasing. So from larger grains to intermediate to sand, then silt, and finally to clay. And if with time this type of condition, this type of fluvial energy condition, river energy condition persist, so in T1 time, this time of deposition you will get. In T2 time, if the river energy conditions remains fixed, then above this large size particles, you will again gain some large particles. Above this sand, you will again get some sand size particles, and above silt or clay, you will again get some silt or clay size particles. But suppose if a river energy condition increase, suppose if a flash flood occurring there, then the energy condition is much higher of the river. So all these larger particles in T2 time, they will carry it further downstream. So above these sand or pebble grains, you will get the cobble or boulder grains. Above these silt and clay grains, you will get the sand grains. So the energy condition with time is fluctuating in that case. So if the energy condition remains constant for a long time of any deposition medium, you will get this type of deposition where you can see all the sedimentary grains, all the sedimentary sand grains are almost equal in size. There is no size variation. Whereas in the right figure, you can see that there are different sizes of grains. Some are coarser, some are intermediate, and some are smaller. So that indicates that your depositional depositional energy condition is fluctuating with time. Now next is the called the fabric, which means that is the arrangement or packing of the particles. Now during some energy condition, whether it will be fluctuating or it will be constant for a long time, the sedimentary grain are deposited. Now how they deposited, what is going on after their deposition, how they are arranged, that is known as the sedimentary fabric. So there is two things, one is packing, another is arrangement. So packing is basically how the sediment framework grains or sedimentary grains arranged among themselves. Now this packing is largely dependent on the grain sizes and shape, and also sorting. Suppose these grains are of large size grains. Okay, so these large size grains can show a type of packing, whereas in the right figure you can see that here along with the large size grains there are intermediate size grains and finer size grains. So here these finer size grains can be incorporated into the empty spaces within these large size grains. But here, as there is no other size class of grains, then only these large size particles are remained within the depositional condition. So no intermediate uh, grains within the void spaces of the rock. So there is ample number of empty space within the sedimentary grain deposition if the particles are all of equal size. That means here the sorting is high, but if it is ill sorted in the what in the right hand picture, in the B picture, you also, yeah, sorting is poor. So during deposition, in the intermediate spaces of these large size grains, these intermediate pores or void spaces, these are filled up with the intermediate size grains or finer size grains. So your amount of empty spaces will be reduced when the sorting is poor, but amount of empty space is high when the sorting is good. Now shape is also a factor. If you suppose you are uh, putting all the footballs in a stack, so if some footballs are putting one after another, then there will be, as these are circular grains or spherical grains, so almost one football is came into contact with other football in a point. So there is ample amount of intermediate spaces within the grain. But if you put some tabular sedimentary grains, suppose you are putting a book one after other, so within these two books, as the grains are flat and the above grain is also flat, so a maximum surface area of two grains are came into contact with each other. So thereby the empty spaces within the tabular grains is far less compared to a spherical grain. Okay. Now these spherical grains can be arranged in two types. One is the cubic packing, where one grain is above the other grain, like this one. Here this grain is above uh, occur this grain. So like this way, this is known as cubic packing. And the other type is rhombic packing, where the above grain occur in between the bottom two grains, that is this grain and this grain, the bottom two grains occurring like this, and the above grain occurs over but in between two grains, that is in contact with the two grains in a point, or in 2 points with the contact, that is known as rhombic packing. Now what happened due to these two types of packing? When the grains are in cubic packing, the empty space within these grains, these are the void spaces, this is the called as porosity or pore space. This empty space percentage is about 48%. But when the grains are in rhombic packing, that is the above grain occurs in between the bottom two grains, then the empty space is reduced almost 50%. Here in case of rhombic packing, your porosity value or the empty space percentage is reduced to almost 26%. So with respect to the packing, rhombic packing is much more tight packing found in rhombic packing compared to cubic packing. And in nature, we will get always rhombic packing. Cubic packing is theoretically possible but not in natural condition. Here you can see that as I already told you, that packing is dependent on shape also. If tabular grains are there, there will be less amount of empty space. Also the alignment of the grains, suppose these uh, spherical three grains, within them a large rod like grain occur inclined way. So this rod like grain inclined way occurring does not allow the above grains to settle below it, so a large number of empty space may remain below the rod shaped grains. So their alignment is also important thing in determining the empty spaces within the grains. Now this packing is modified after the deposition with increasing overburden pressure. So suppose if we consider then when the grains deposited, grains are isolated with respect to one another. That means the grains are floating. Each sedimentary classed particle is not in contact with each other at all. These four grains you can see are not in contact with each other. So these are called floating grains. Now as the overburden pressure increased, these grains came close to each other and they touch each other in a point. So that point is known as the contact between those two grains at that time is known as point contact, when the two grains touch in a point. Now with increasing overburden pressure, the contact area between two grains will increase. So after point contact with increasing pressure, the grains touch along certain planes. Then we call them as long contact or line contact. With more increasing pressure, the contact area between two grains starts melting. Now, the grain in which the melting point is faster, within this grain, the above grain incorporates, and we will get such type of convex or concave type of grain contact between two grains. This type of contact is known as concave or convex contact. But mind it, in this case, the melting point of two grains are different. The melting point of this grain in which the other grain is incorporated, this is melting point is higher, while the melting point of this grain is lower. And the last one is called as sutured contact, while the melting point of grains are almost same. So here both the grains are melted and they formed such type of zigzag nature contacts between two grains. Okay, so this is known as sutured contact. Keep in mind that this type of contacts, from floating grains to point contact to line contact, concave contact, contact to sutured contact, this type of increasing contact area between two successive grains is occurred due to much and much or more and more overburden pressure. So as overburden pressure increase, contact area between two grains will increase. Okay. Last is the orientation of the grain. As I already told in the packing slide, that the orientation of grains is also important to describe the fabric of a sedimentary rock. Here you can see a elliptical grain is moving with current. Now, if the current velocity or energy condition of the medium is low, then this elliptical grain is moving along the along the bottom substrate. That is, the flowing medium is not able to move it by saltation or by suspension, because depending on the or compared to the energy condition of the flowing medium, with respect to the gravitational and frictional force of the this elliptical grain, this gravitational and frictional force of this elliptical grain is higher compared to the flowing current of the medium. So that is why this type of grain is moving along bed load. So whatever the when energy condition is low, a elliptical grain is moving uh, as bed load. That is, a grain when moving as bed load, then what happens? When a elliptical grain moving as bed load, then the major axis or the long axis of the grain is always perpendicular to the flowing direction. You can see that it will roll along this surface, along the long axis. So long axis, during after deposition, the grain will deposit in this manner. So when a grain, elliptical grain moving as bed load, the long axis of the grain is oriented perpendicular to the flow direction or current direction, whereas the short axis of the grain is parallel to the flow direction or current direction. But the same grain, if it moves as a floating grain, that is in suspension, then like a ship, then its long axis or major axis is parallel to the flow direction, and its short axis is perpendicular to the flow direction. You can see that a ship is moving along the flow direction with its long axis parallel to the flow. That means the ship is floating with its long axis parallel to the flow direction. The same thing, this elliptical grain is moving with its long axis parallel to the flow direction and its short axis perpendicular to the flow direction. So whenever a elongated grain, elliptical grain is moving in bed load movement, bed load transportation, then its long axis is parallel to the flow direction and short axis, a long axis is perpendicular to the flow direction and short axis is parallel to the flow direction. And whenever any elliptical grain moving in suspension, its long axis is parallel to the current direction and short axis is perpendicular to the current direction. But when this type of grains deposited in a haphazard fashion, then there will be no such preferred orientation. You can see that the grains are oriented in a random fashion. So this kind of uh, deposition indicate a random deposition. That means it is not suffered any prolonged transportation within the flowing medium. If the grain suffered any prolonged transportation, then they will be definitely oriented. Depending on the bed load and depending on the suspension type of movement, the grain shows different orientation of its long axis with respect to the flow direction. Now coming to the porosity terminology. What is porosity? Porosity is the empty or void spaces present within the rock. It is defined as the volume of the empty spaces. These sky blue portions are the empty spaces between the red dots. The red portions are the grains. So the volume of these empty spaces divided by the volume of the total rock. Now this porosity is dependent on the packing. If it is showing rhombic packing, then porosity is high. If it is showing cubic packing, porosity is high. If it's showing rhombic packing, then porosity is low. Porosity is also depending on sorting. If sorting is high, that is all the grains are of equal or same sized, porosity is high. If sorting is poor or ill sorted, then porosity value is low. Porosity is also dependent on grain shape. If grain shape is spherical, then empty spaces are much higher in amount or much higher in volume, while the grain shapes are tabular or bladed, there is less amount of empty or void spaces, which is a measure of porosity. So porosity is dependent on these three factors. Okay. So poorly sorted angular sediments have small spaces and can trap more fluid, can trap less fluid, whereas well sorted rounded grains have more empty spaces and can trap more fluid below the subsurface. Now porosity can be of two types. The first one is the primary porosity, or it is often called the original porosity, that is the pore space present during the deposition of the sedimentary grains. So when the sedimentary grain deposited, then only the empty spaces formed within the sedimentary grains is known as the primary porosity. Apart from this, there are some secondary porosity, or it is called induced porosity. This porosity is defined as a pore space developed or formed after the formation of the rock. You may heard about the terminology folding, fracturing, faulting, joints. So during those diastrophic events, often some cracks or fractures generate within the rock space, within the rock. So those fractures or those empty spaces, they are generated after the formation of the rock during any diastrophic event. So those kinds of pore spaces are known as secondary pores, and the porosity is known as secondary porosity or induced porosity. Now there is another division of porosity that is known as effective porosity and ineffective porosity. The effective porosity means, you can see in this picture that there are lots of empty spaces or lots of pore spaces within the sedimentary grains, but this pore space is connected with the bottom one, and it is connected with this bottom one. So a fluid poured here can be moved easily from this way to the bottom point. So this type of pore spaces or this type of porosity is known as effective porosity, in which the pore spaces are interconnected with each other so that fluid can pass from one point to another point. But in the left side, you can see a pore space where this pore space is blocked from all sides. That is, here a pore space and empty space is there, but if any fluid occur there, that fluid cannot be moved in any direction because all the sides are blocked. So this type of pore space or this type of porosity is known as ineffective porosity, because the fluid trapped in this pore space cannot move from this point to any other point. Okay, so whenever a fluid can move from one pore space from one point to other pore space or other point, that porosity is known as effective porosity. But whenever a rock having porosity but that pore space is not connected with the surrounding pore spaces, that pore space or that porosity is known as ineffective porosity. The next property, which is known as permeability, which depicts the ease of permeation of a fluid within a rock. That is, it is the property of a rock which allows fluid to move from one point to other. That is known as permeability. That is how much amount of fluid a rock permits to move from one point to other. And this property, that is permeability, is dependent on some textural properties like grain size, grain distribution, that is sorting, shape of the grains, packing of the grains. So basically these four factors affects my porosity value of the rock, and this porosity is directly related to the permeability. So more and more porosity, generally more and more permeability. And also there are other factors like the amount of clays are there, because you know that clay have a cohesiveness property which retains the fluids around its surface. It does not allow all the fluids to remove, whether the rocks bear any secondary porosity and the overburden pressure, also these things. But remember that it may possible that a rock have high porosity values but not permeable at all, because for permeability, that is for moving fluid from one place to another place, it is needed that the pore spaces are interconnected among themselves. Now it may possible that a rock host lots of pore spaces, but those pore spaces are not interconnected among themselves. So in that condition, although the rock hosts lots of empty spaces and can host lots of fluid there, but as the pore spaces are not connected with each other, those fluids are not able to move from one place to another. So that means permeability is low. So you can see in this figure that grain size is plotted in x-axis and permeability value is in the y-axis. Now for the same grain size, if sorting is increasing, follow this arrow. For medium grain size, if sorting is increasing for the same grain size, my permeability value is, that means porosity is increasing, that means permeability value is also increasing. So gravel have high porosity and high permeability, sand high porosity, medium permeability, because grain size is low with respect to gravel. Mud high permeability, porosity but low permeability, because the pore spaces are not interconnected in mud, and also the cohesiveness force. Granites, it's a igneous rock formed by crystallization of a molten material, so no pore spaces within the rock, so that is why low permeability. Fracture granite, that is secondary porosity is generated during any diastrophic event, so those fractures or those voids are now becomes the way for transmitting fluid from one point to another. So that shows fracture granite shows high permeability. So this fracture formed due to some secondary diastrophic events. So that's all for sedimentary texture. That is a brief introduction. Hope you can all understood. Goodbye.